my screen here. So 1 second, give me. So you have to come up with the two research ideas per group. And I have already made the groups on the D12. So you should coordinate with your team. I'm sorry, what is this? Team members. The research project should be related to vibration, acoustics, data analysis, time, frequency, engineering, design, etc. It's a series of ongoing research projects that span the entire semester. The final paper is due mid. So this is the beginning of the research project. Like this first assignment is a series of all the coming assignments. So in this first assignment, you will select a project. I gave some of the examples which are closely related to what other students did in the past. For example, resonance. How does resonance frequency vary with different material properties and structural geometries? And damping ratio. Actually, these are the two, not two numbers, but just one number. Somehow this is software is automatically giving another. So, but acoustics, vibration analysis. So I would suggest you go home and when you talk to your team members, which selection do you prefer? You might have your own. You have freedom to choose which paper you want to work on. Can you do that at home this week? Coordinate with you. I think you are working together, and you are and another guy. He's not here because some reasons, but you are three working together. And I have made a group of students. Can you see this on D12 that you are grouped together? So you are good. You can see it on the D12. No, can you see it? No. If you go to the D12, so if you go to the D12, I think in others you see the groups. Can you go? Do you see the tab other and the groups? Do you see it? So you found your group members there. Okay. Now it's not difficult. You come up with two ideas and we will discuss together. But I would suggest you when you submit this homework, submit it like I gave like a 90% weightage to idea number one and 80% weightage to idea number two. This will be your preference. Then I'll give you my feedback. That because with the 4 months or 3.5 months left, that's the time span. I want to select such a project which could not be that difficult, which could not be that easy. Just it will cover the whole semester easily. Okay, let's go with the next thing I want to share with you. So, chapter 3. Free response with the single degree of freedom. We will study multiple degrees of freedom later down the road, but today we will study about the single degree of freedom. Okay, I'm giving give some examples. So let's start from the okay. Project out the chapter outlines are here. First order response. For example, I give you an example. If you see a problem, physical system, and how do you go from physical system to mathematical equations. So let me give you one example. Okay, I give you one example. Suppose this is a block of mass, and this is on a table. Okay, um, it has friction. So force. So when you this is a block of mass, and when you apply force and in this direction, so what will happen? It will start moving to the right, and there is a friction in terms of, we call this as a damping coefficient. Friction is known as the damping coefficient. Okay, so can I write down? Do you remember? Okay, you might have studied about this symbol. This is known as the damper, and this is known as the spring. And you might know that the force due to the damper is c. Force due to the damper is c times velocity, or you can write down c times x dot. It doesn't matter. If you write on x dot, time derivative of position is velocity, and force due to the spring is k times x. Agreed? So what I'm going to show you, there is a friction force due to the damping between the like I will say friction acts like a viscous damping. Agreed? So I can write down, let me write down like this, cv. Okay, let's for the moment, let me write down in terms of variable v. So now it's moving in this direction. Now, the Newton's second law. When you are deriving the equation of motion, you will start with the Newton's second law. Newton's second law states all the forces on the left hand side, they are equal to mass times acceleration. So mass times acceleration, since it is in terms of variable velocity, so can I write down like this? And now on the left hand side, I'm going to show you. Look, this is my positive direction, because I'm assuming that my coordinate, right coordinate, is positive. X is to the right is positive. So look over here, forces, this force and this force. Now let me show you the direction of the damping force. Would it be in the direction of motion or opposite to the direction of motion? Opposite. You see, because it is resistance. Viscous damping is resisting. So can I write down a negative? Look over here, I can write down negative c. So why am I writing now? Because it is opposite. So this is applied force minus friction force equals to mass times acceleration. You see my point, guys? And now if I rearrange it, if I rearrange everything, can I write down like this? M, I'm sorry, let me write on first step, then I will show you. Can I plug in the number, this formula in place of this F sub C? I can do that. M, sorry, this is F minus C times V equals to mv dot. Now, if I rearrange it, that I can rewrite here acceleration term, first order derivative, velocity term, and then equals to force. So it is the differential equation of motion, first order. Okay. Now, according to our knowledge, which we possess already, we know that a standard form in the first order equation, a standard form. Let me write down the standard form here. Standard form of first order differential equation of motion. So time constant times order, some constant here. So maybe I can write down here just like this. And the coefficient for this velocity, the second term is 1. This is coefficient is 1. And then this is known as the time constant. And I can write down this equation. The solution velocity at any time can be a e to the st, where s is the root, and I can write down is in terms of s equals to 1 over negative, sorry, negative. You know why? Because if I don't plug in negative, what will happen? So if it is positive, it will grow. And positive means time passes, exponential function keeps on growing larger and larger, and it is known as the unstable system. But we have to have a negative exponent in order to bring it to the zero position again after a certain time, which is maybe 4 times the time constant. I talked about the time constant last lecture. 4 times the time constant, you get 98% position to the mean position, which is usually. So this is the growing. So when we have positive exponent like e to the s, maybe e to the st, which is, hey, s is positive. But if s is negative, is a so hey, in this case, what will happen? So I can write here v sub 0 e to the negative t over tau. This is the solution of the first order from this standard form. Okay, look, if I know what is my initial condition, usually it is given in the question, it is given. And can I find out the time constant from here? From the standard equation, look at the first order coefficient v dot. The coefficient of v dot is the time constant. Only it is time constant at that moment when you have coefficient of 1 with a variable term. So if you compare, look, if you compare this equation with this standard equation, how can I bring 1 over here? I will divide the whole equation by c. That's it. So let's do this. Let's do it together to see the solution of this equation. So I'm going to show you. Let me write down the same equation and bring the coefficient of the variable as 1. So I will divide the whole equation by v dot. Now on the right hand side, this is a force response. So you will make, you see the standard, this is the homogeneous equation, which says that the right hand side, it's a free response because our focus is on the on on the free response. We will study the force response later. This is the right, so you have to make the right hand side equal to 0 in order to get this, apply this solution. This solution is only applicable when you have right hand side equal to 0. And if it is a right, if it is not 0, it's known as, you will study later, it's known as steady state response. Steady state response is different than the free response. Free response is you right hand side, you just give initial condition. That's why I wrote down V sub 0. Suppose um, uh, if you move a spring, the mass up until like 1 centimeter up, and just leave it, it will start, it come back, oscillate and stay there. So it's a free response. This is the free response, and we can apply the equation. So let me write down this equation like this. So what now can I apply this? Velocity equals to V sub 0, or V0 domain e to the, what is the time constant? Good job. The coefficient of velocity dot, the first order term, that is the time constant. So can I write down T over M over C? And if you rewrite M over C, can I write down like e to the negative C over M times T? Now look, if now the negative sign is already there. Now C over M, if it is positive, it means system will come back to the stable condition because negative sign is already there. But if like it's known as a stable system. But if this coefficient of T, if it is negative, if it is negative, then negative multiplied by together is positive. So that is the unstable system. And how do you draw the unstable system? Let me show you. Let me show you graphically. Over here, if I show you graphically, so velocity here and time here, and you will tell me, okay, I'm gonna draw two plots. You will tell me. I'm gonna draw two plots. This is my uh suppose this is my another. Oh, 1 second. 1 second. I wanna draw it here. And this is graph number 1. And this is graph number 2. Graph number 1. Which one is a stable graph? Number 2. You remember in the last lecture, I talked about the constant. You see, I drew this plot to show you the time if the system comes to 0 position. If you give initial condition maybe 10 meters or 10 meters per second the velocity to some motor, whatever it is, it comes to rest after some time. Okay, let's say. So, okay, let me show you a diagram here in our book. We will come back to chapter 2 later. I want to finish a little bit some of the vibrations and come back to dynamics a little bit later. So look, have you understood this plot? You just have to graphically understand. This is growing exponentially. It's unstable. And when you have this condition C over M is 0, it's a constant value. And when you have this 0 and it's positive, it comes back to the mean position. I want to show you one more thing that if you take this, um, equation of motion, which is this one. Do you know I think there is a Laplace transform table. Do you know about Laplace transform? Laplace table form sheet. This is the Laplace transform of the first order derivative. And the second order derivative. You will study this Laplace transform in detail in chapter 5. Look, this is the model. And I explained it that when you are dragging a mass, it creates some friction that is a negative coefficient, uh, damping coefficient. So that's why I'm drawing that in the form of an equation. Now look, over here, I want to apply this. I want to apply this over here, the Laplace transform. So keeping this right hand side is 0. And what is the Laplace transform? Initial conditions are assumed. So initial condition, I'll show you in a bit. This is MS. Can I write on MS, big V, S domain C, big V, S. So then you have this initial condition. For this one, I can write down negative initial condition as written like this. Okay, now look over here. So V of S in S domain is outside the parentheses MS plus C. So V of S. So this thing MS plus C equals to 0. So S equal to minus C over M. Is the same thing I wrote down here. Because S equals to 1 over the time constant. So can I write down time constant as M over C? Agreed? So V of S, yes. Look, this is already there. This is the initial condition. So it's there because I just added the big V's together. So now look, can I write down here like this? V sub 0, V of 0, M is outside, S plus C over M. So now if you take the inverse Laplace, so V of t equals to V of 0 e to the negative C over mt. Because we know that the Laplace transform, sorry, inverse Laplace transform of this term equals to e to the negative at. You might have studied this earlier, but you can revise it. Whatever method you use, you get the same answer. So let me show you one question. Let's do one question together. I think this is our. Okay, please draw the equation of motion for this mechanical system. The question states here, look, the question here, it states find out the solution of this. Let me read it to you, okay? In the figure 3.13a, by the way, this is figure 3.13a. Okay. Mechanisms such as cam drives the left hand endpoint. So this is the endpoint and keeps going forward and backward as a function of time. Derive the equation of motion of the system in terms of the displacement x1. So we have to derive. Does it say to find the solution? Okay. We will find the solution. I will find out what is this solution of this derivative. So let's do it together. Okay. This is when you see such a, you will see many of problems example, you will see such a sign. It is nothing but the displacement degree of freedom, that this node, it is moving with a displacement, the coordinate is x1. It is starting from 0 and at this moment it is going to the right will be positive, and this is another You see another degree of freedom. So the book has some books they don't put it. Some books they write down like on top of this and say degree 1, and this is say degree 2. So it depends. It doesn't. It is not a big deal that you write down this way or the other way, but these are the degrees of freedom or the generalized coordinate. You will also study generalized coordinates, which completely define the motion of the system later down the road. So let me show you. I want to show you that what is the equation of motion. So can I take this node, which has this motion to the right is when this node move to the right, it's a nodal mass. Nodal mass means mass is 0. Then the spring will exert, push this to the left. So what is the force due to the spring? Minus kx. And when this node moves to the right, the damper will also bring it to the left. And the damping force is c times. Now here comes the trick part. Look, this end is moving. This end is also moving. So how will you find the net velocity? Net velocity. You have to find the difference. Okay. So the way I will do, I will take the coordinate which is for the nodal coordinate, the mass coordinate. I will write down that first to be consistent. In future, when you are considering the mass, that the coordinate of the mass you should write down first. So what is the coordinate of the nodal mass? X1. So what is the velocity? X1 dot will come first, and then comes the other end velocity. What is the velocity given in the question? V. It is the symbolic expression. Can I write down negative V? So this is the, and negative sign. Why do I write down negative sign? Because my coordinate is positive to the right. Can I write down the equation of motion? All the forces, they are equal to mass times acceleration. Yes. Velocity of the other end of this end. Okay. So look, can I write down like this? Minus kx1. This is my C. Now, guys, the right hand side is the mass, but do we have the mass of this node? No, we don't. So can I write down like equal to 0? Because this is the nodal mass. So I'm interested in, let me show you this standard form. Let me show you this standard form here. Tau. Okay, guys. So over here, I want to bring my whole equation in this form, and then I will apply the formula. Look, how can you help me in terms of, let's do it together, okay? Can I write down here negative cx1 dot minus kx1 plus cv equals to 0? And when I bring this to the right hand side, this becomes negative c. I just rearrange this one so negative is cancelled out because it is distributed in every term. So now what else? How can you make this as positive? Sorry, how can you make it as 1? Divide the whole equation by letter k. So look, k, k, k. Now in order to have the homogeneous equation, the right hand side should be 0. So then the new equation is c over k x1 dot k x1. And what is the solution for this equation? I already told you that if you see such an equation, the solution exists here. This is the solution. For the standard equation, first order equation, the solution is this one. And now let's find out our solution looking at the solution of the standard first order equation. So what is my tau? Can you help me? Good job. You see, now you have understood. C over K is our this time constant. And I'm going to write down my solution as x1 at any time. The displacement of this node at any time is the initial displacement minus k over c times tau. So this is my answer. So if k over c is positive, the solution is like this. And usually if it is negative, then it is not a stable system. Have you understood how I solve this question?
Professor, I have a quick question.
Yes.
In the expression you have written above, the c over k x1 dot plus k x1 is equal to 0, should that k for the x1, should that go away since we divided the whole equation by k?
Yes, because we normalize the x1 term. That's why we make it 1. Oh, I'm
Okay.
sorry. You are right. I shouldn't have written down this. Thank you.
Mhm.
That was a good pick. Okay, now have you understood how to find out the solution of the first order equation of motion? So my whole objective is to teach you how to go from physical system. Physical system consists of 3 elements: mass, damper, spring. Mass, damper, spring. Mass, damper, spring. Sometimes they are angular damper, angular mass. Angular mass we call it as mass moment of inertia. I will talk about it uh, in today's video, and I will share with you a video I already made, a video for rotational motion. You have a question? Yes. Yeah, this is the good question. Look over here. This is the point. So maybe look, it may be like a big cam. We don't know. Usually the big cam, it keeps on rotating and keeps on pushing forward the damper backward. It's a cam operated system. Look, mechanisms such as cam drives the left hand side. And when you push the left hand side, the right hand side also moves. So you will study. If I were you, I will look closely at the statement of the problem and then try to understand, collect the data from there, and then find out the answer. So let's do one more problem, then I will move to the next topic. There is just one damper. So the other one is spring. So the other end is also moving. X X X1, yes. X1 is also moving to the right. Okay. Now we have to take the net velocity. Okay, let's do one more problem here. I'm going to open a homework. Sometimes the research homeworks and their homework, I will still give you some time interval between these two homeworks, but you have to do both. Since the research is a combination, you are working with these two team members, okay? These are your team members and you're working with together, so come up with the. So I was telling that when we research paper, they say we have to go throughout the semester, entire semester's research going, so goes side by side with the, because I mentioned in my last lecture, he says that our research is 15% of our, I believe I mentioned this in my last lecture, 15% of our credit. So you will write down a nice paper. Please come up with one design, two design ideas, and then we will refine it, and then I will give you my feedback. We will select out of those two as a team, work as a team. Just two ideas per team is not difficult. And I mentioned, you see, I gave you a lot of examples, look, of the project ideas, and try to use, select that one in which you use have you can use MATLAB, because MATLAB is a tool which at this stage you should know how to do simulation in MATLAB. Just plug in the theory, find out the answer. Okay, let's do the next question. I want to just go ahead and solve this one for you. And the good thing is that MATLAB is available for our students for included in your package. Okay, look, this is the first order equation of motion. Let's do one problem here very quickly because it's not difficult. Look, let's obtain the free response of the following models, determine the time constant. Let's do first question. 8y dot plus 7y equals to 0, and initial condition is given. Look, the standard equation is tau y dot plus y equals to 0, where y of 0 is given, the initial condition. And I can write down y of t equals to y of 0 e to the negative t of tau. This is the solution. So can I write down, first of all, I would divide the whole equation by what? 7. You see? So we have to make our actual equation with the standard equations. This standard equation does not have the coefficient of y, which is just 1. It has, but it is 1. So can I write down 8 over 7y dot plus y equals to 0. And now just use this equation. Y t equals to y sub 0 6 e to the negative t over tau. Tau is 8 over 7. 8 over 7. Agreed? So if I rearrange this, can I write down like this? C e to the negative 7 over 8 t. This is your answer. You see one line answer? So for free response, whenever you see the right hand side is 0, is homogeneous equation, and it is known as a free response. Mean it's not steady state response. So let's do one more problem. By the way, I will be able to grade your quizzes this week. I need some time. Is that okay? Now this is the rotational motion. We studied about the translational motion earlier. Now we are moving towards the rotational motion. So what is the Newton's second law in rotational motion? Let me show you. The Newton's second law states that all the moments, all the torques, they are equal to mass moment of inertia times omega, or omega dot, sorry, which is, or alpha. Some books they write down alpha, or some books they write down x double dot. They are the same things. Alpha is the angular acceleration, x double dot is angular acceleration. I'm sorry, this is not x double, this is theta double. In angular rotation, x is replaced by theta. You see? So correct me if I do some mistake, you can correct your professor. Okay, let's do it together. Okay. So the question states shows an axle driven by a torque T. So look, this torque is being applied and supported by the journal bearing. And the bearings, they have the friction. Journal bearings, they have the rotation damping coefficient C. So it has a damping coefficient. The symbol of damping coefficient is C. And the axial inertia about its axis of rotation is I. This I is given. It is the inertia, mass moment of inertia, which is mk square, radius of gyration times the mass, or if it is a pendulum, you can calculate it r square dm or mr square. We will talk about it later, but I'm just reviewing how do you find the mass moment of inertia of a rotational motion, uh, rotational motion. R is the distance. So we can represent this system abstractly with the hashed symbols. Okay, derive the model equation of motion. Okay, now can you tell me if you plug in? Look from here. This is the first figure is the free body diagram. It's a free body torque. Applied torque is positive. Do you see the resistive torque? I would say negative. Book says see the books takes the magnitude, but I'm taking algebraic magnitude because on the left hand side I have to do like this because applied torque is clockwise and the resistive torque is stopping that move. So it is negative. It is trying to stop the resist the applied torque. That's why it's the journal bearing. You see about the journal bearing, there's a difference between journal bearing and the ball bearing. Journal bearing is like a bushing. Okay, it has some friction between the contact surfaces. So it's a negative sign. Do you agree with your professor? Okay, now look, now this is the condition. So I want to show you for this one, the right hand side. Let's do this. Let's rearrange it. Okay, can I write down the first order first, then the zeroth order like this? Now look, the right hand side for the free response. What is the condition for the free response? The right hand side should be zero. There should be no torque. So can I write in like this? Yes, it's the same. So you see, I can write down like this. I'm just because I already solved such questions, so I'm going to skip one step. You can understand that I made the coefficient of the variable as 1. Now omega at any time is omega 0 e to the negative t over tau, and tau over here is I over c. So can I write down like this? Omega 0 e to the negative t over uh, I or C. So it means if I plot it graphically, look at 0 time, the object starts its motion. The shaft starts its motion with a certain angular speed. Angular speed is radians per second. Agreed? Like it has some value, and then it goes down with a time constant here, time constant which is I over C. And it covers like over here it is like 37%. I discussed this earlier. So let's move to the next question. Have you understood this question? So I've given you the idea how to do the translation, how to find the equation of motion of the rotational motion. Okay, let's move to the next. And I want to show you one more thing, that there are certain formula which you have to understand. And when you go home, study the book. I'm gonna My lecture would be aligned. If you want to get grades, your book should try to read those topics which I give lecture about. Some topics I don't teach, which you don't have to study. You can just learn on your own, but I will not probably give you in the quiz or test those topics. But I try to, therefore, I skip some of the homework problems, and you can learn on your own, but I will not assess you from those other than the homework problems to make your life easy. So, power dissipation of the damping. In damper, you have friction, we lose power. Power is the rate of energy, or I can write down it is for a small time rate of energy is power. And I can write down here, it can also be written as power equals to force times velocity for the translation motion. Agreed? How about if I have a rotational motion, like if I have a shaft, it is being supplied with a torque and rotating with a, then the power is torque times omega. For rotational motion, the formula is torque times omega. For translation motion, power formula is force times velocity. And if you have a resistive torque, C omega. Can I write down for the power dissipation for the damper? Look, what is the torque generated by the damper? C omega, right? And can I plug in C omega over here for the damper, right? C omega square. So the power dissipation in damper, it is C omega square. Have you understood? Another small concept I want to bring into your notice, that if you have two gears, then they are meshed together, and then gear 1 is rotating over here, gear 2 is rotating counterclockwise. So the ratio from gear 1 to gear 2 is known as the gear ratio. And we know that the velocity at the meshing point, it's a linear velocity or tangential speed. What is the formula? Do you remember in your undergraduate studies, what is the formula for velocity tangential velocity? V equals to R. If I give you R and omega, V equals to R omega. You see that? Yeah. It's so that velocity is same for both meshing point. At the meshing point, that is the contact point over here. So it's the same. So can I write down for R1? This is my gear 1 and this is my gear 2. Can I write down like this? So if I can write down like this, what is the gear ratio? Omega 1 omega 2, or R1 R2 over R1. Can I write down like this? And similarly, in the book you will study that the 1 over n or n square, 1 over n square, 1 over omega 1 square over omega 2 square, omega 2 square over omega. This is just a rearrangement. So I'm going to show you one question. Let's do one question. It's going to help you. It's going to help you to derive the equation of motion for the gear train. Okay, let's do one problem here.
Has this homework been released yet? The
Oh,
D2L?
I'm going to release it today.
Okay, thank you.
Remind me if your professor forget, but I will keep it. Thank you for asking. But let me show you the next question here. By the way, I released another homework regarding the research. So I was just doing that part first last night. I was working on that, but I'm gonna open this. So, what do you suggest me? How much time do you need to do this homework? Like maybe 2 days extra more than the research question?
The the
Yeah,
research the research project is all those research homeworks, are they graded individually or is the
yeah,
project graded once at the end?
yeah. It's a group project. Every semester, every assignment is a group task. So you will coordinate with your group member. Do you see your group members?
Yeah, I'm gonna look at right after this.
So it's not an individual from any homework for the project related, it's a group assignment. And we have just 2 members in a group. And by the way, over here in class, we just have 5 people. So I joined 3 of the students together. So you are lucky that you are 3 people working together. You are lucky.
Quick question, Professor. Is the regular homework group or is it still solo assignment?
That's a good question. It's individual because we want you to learn the material individually. So, but you can collaborate, but it's better to submit individually. Okay.
Okay, thank you.
Research is a group, but the regular homework is not grouped. Yes, submit as a group, or you can select your leader. I will say this time you will be the submitter, then to some next one is you will be submitting, he will be, she will be. All right, let's go to the next question. So this is the gear train, and you see one gear is rotating and torque is given here, and then you wanna derive the equation of obtain the equation of motion of the system with the torque T1 as the input. Assume there is negligible elasticity in the system and that the damping on the input shaft is also negligible. In order to solve this question, I want to go to the background a little bit. What is the kinetic energy of the gears when it is rotating? Kinetic energy is for the let's start from the very beginning. This is for the translation motion. But for the rotation like this gear, for the rotational kinetic energy, for the rotational motion, it is half I omega square. And I will show you the kinetic energy is given like this, and I equivalent when you combine these two i's together into this form. Since we did not go over to the what we call the chapter 2, but when you combine these two together, you will see that the I equivalent, it is the I1, the mass moment of inertia of this gear 1. And since there is a gear train, sorry, they are meshing the gear teeth, and the mass of moment of, I can write down like this: I2 omega 2 over omega 1 whole square. Or I can write down like this: I1 plus I2. Since I know that 1 over n square is like this, So can I write down 1 over n square like this? And this is true that since this is a master class, so I would leave it to you. How is it equivalent to this one? Can you do when you go home that I'm trying to reduce, but I have made a video on YouTube. How is it equivalent to this one? You can watch it. I will share with you. Okay, let's do this kinetic energy total. What is the kinetic energy total? Look, I want to show you right now. I can explain it now. Look over here. What is the kinetic energy of gear one? Gear one, it is, let kinetic energy of gear one is half I1 omega 1 square, and gear 2 half I2 omega 2 square. Okay, what is the total kinetic energy? Total kinetic energy would be the sum of these two shafts or two gears. Sorry, this is sum of this, so half I1 omega 1 square plus I2 omega 2 square. So now look over here, I want to reduce it to just shaft. Uh, this is shaft 1. Agreed? This is shaft 1. Torque 1 is being applied to shaft 1. So I want, how is it equal to? So I want to derive from here. I want to take omega 1 square outside. When I take omega 1 square outside, I'm left with over here I2. And what is that? Look, it's the same thing. I just explained it rather than you study by yourself. I explain it now. Have you understood how did I get I equivalent? You just take the omega 1 outside and omega 1 square outside, and this is my I equivalent because I know that the I equivalent for the kinetic energy of the equivalent is half I equivalent omega 1 square. You see, and whatever it is here, it is I equivalent. And what is that? It is equal to I1 and I2 over N2 square. It should be square. I forgot. But have you understood how did I write it down? Now it's very easy for me and to solve this question. And one more thing, when you are bringing this damper from the second gear to the over here, you will do the same. How you have to divide that because the P equals to C2, I would say C omega 2 square. This is omega 2 square. Agreed? But is C equivalent? Is it omega 2? No, it is omega 1. So how can I write down C as C equivalent? That is, I can write down like this because I know that C equivalent omega 1 square, it is equal to C, I would say C2. Let's say C2 omega 2 square. So can I write down C equivalent equals to C2 omega 2 over omega 1 square? Can I write down like this? And what is this? Look, what is this? Omega 2 omega 1 square is a 1 over n square. So I can write down C equivalent as C2 over n square. You see my point, guys? So now the whole gears have been, this is now I equivalent, this is now a damper equivalent, C equivalent here, omega 1, this is omega 1, negative sign. So I can write down the whole equation like this, I equivalent omega 1 dot, it is equal to what? This is torque plus omega 1 is C equivalent omega 1. This is how you write down all the torques from this equation of motion. I'm writing that all the torques, they are equal to I equivalent times omega 1 dot. Agreed? And then you have to, yes. No, it's given. Look, it's just one damper. Look, is in between the meshing area. You can attach it at the end. There is just one damper. Yes. Plus, this is plus sign. Oh, oh yeah, you are right. There is a mistake. I forgot. There should be negative sign. Thank you. You see, so now I have to rearrange it. Look, the first order term now is the equation of the first order. I starting my lecture from the first order. You see, I have made the first order. You have, so I can make the a rotational motion as the first order, translation motion as the first order, and then I can find out the time constant. From here, the same story. We just found the time right hand side, make it equal to 0. And then you're left with I equivalent over C equivalent as the time constant. Agreed? And omega 1. So what is the formula? Omega 1 at any time is omega 1 at 0. Look at e to the negative t over tau. Tau is what? I equivalent over C equivalent. So that's how you solve this question. Thank you, guys. So I'm going to share with you some more videos. When you go home, watch them, please.